The purpose of this video is to give you an example of solving a KEQ problem and discuss the stresses from Le Chatelier's principle. We start out with a two-way reaction, and I'm going to actually rewrite it so it's a little bit bigger. Hydrogen gas plus carbon dioxide gas reacts to form water in the form of gas plus carbon monoxide. But this is a two-way reaction, which means that the carbon monoxide in the water can also react to form carbon dioxide and hydrogen gas. The question starts out stating that the reaction is at equilibrium, which means that the rate forward is equal to the rate going backwards, which also means that if we look at the different concentrations of each of these species that are in the tank or flask, they will always have the same concentration at any one moment in time. When we reach equilibrium, the concentrations are the same, even though they're not the same particles that are always there. We can talk about whether a certain side of the reaction is favored or not. The products are favored or the reactants are favored based on the relative concentrations of each. To understand this a little bit more quantitatively, what we do is we develop this idea of the equilibrium constant, which describes the ratio of the concentrations of the products to the concentration of the product of the reactants. Note this is the product of the product concentration and the product of the reactants concentration. This term products is actually the mathematical term products, to multiply. So if we apply that definition to the reaction that we're interested in, we can get the following equation. KEQ is equal to the product of the products divided by the product of the reactants. Now, applying this to the problems that you've been working on up to this point have been pretty easy because you've been just given the actual value of concentration. In this particular case, it's a little bit trickier, requires a little bit more thought. Here's why. We're actually only given the initial amounts and the amounts of the products at the end when the reaction is at equilibrium. That means we have less of the initial amounts of our reactants than we started with. The question is, how much less? Well, the answer is pretty easy because we have a 1-to-1 molar ratio in our reaction, and we can actually just subtract this from that amount. So in other words, if I started out with 0.10 moles per liter of my reactant and I ended up with 0.047 moles per liter of my product, that means how much reactant do I have left? That would be 0.10 moles per liter minus 0.047 moles per liter, which is equal to 0.015 moles per liter. That is the concentration of my reactants at equilibrium. Now that we know all the concentrations at equilibrium, it becomes pretty much plug and chug like all the other problems you've done. We just plug those values into the equation and solve for our equilibrium constant. Now, we don't list units on equilibrium constant, and this one actually doesn't have units because it would be units of moles per liter times moles per liter divided by moles per liter per moles per liter. So those would all end up canceling out anyway. That doesn't always happen, but in any case, we don't actually list the units on our equilibrium constant values. Here are a few other things worth noting. One, this problem could be a little bit more complicated, whereas we may not actually start out with the same number of amounts of reactants, and we may end up with different amounts of products at the end. But there are other ways to keep track of all of this accounting, and we'll learn that. That's what we refer to as the ICE method in some of the previous videos and videos that I'll be doing in the future. A few other things that are worth noting are the three stresses from Le Chatelier's principle. One is concentration. That's pretty much the easiest one. If I increase the concentration of any of these things, then what will happen is these items will run into each other more frequently, causing a shift in this way or a production of these items here. So the concentrations will actually go up if I simply add this without adding any more of this. And we can increase or decrease the concentration of any item. So if I were to decrease the concentration of something, then the collisions between these two particles are going to happen less frequently. The rate going this way would actually slow down, and the rate going this way would be more, therefore causing a shift to make up for the stress, producing more of this concentration here. A second stress that can cause a shift in the equilibrium is pressure. Now, the way pressure works is it's only going to affect the gas. So we have to look at how many moles of gas we have on each side. And remember, Le Chatelier's principle is that the reaction will shift to relieve the pressure. In this case, I have 1 mole of hydrogen gas, 1 mole of carbon dioxide gas, 1 mole of water gas, and 1 mole of carbon monoxide gas. Since I have the same number of moles of gas on either side, I actually won't be able to cause a shift in this particular reaction by increasing or decreasing the pressure. The third stress that causes a shift in the equilibrium position would also be temperature, or temperature change. Now there's a couple ways to understand this kind of a shift that can be caused by a temperature change. One is to actually have a heat term in the reaction. And in a problem like this, or a question like this, is actually really easy because heat ends up being a lot like item, product, or reactant, just the same as concentration. In other words, if I heat this up, that's like increasing the concentration of heat, if you will, which would cause a shift to the left, producing more reactants. If I were to decrease it, okay, then it would cause a shift to the right. But yet another way to have to worry about the changes in temperature in a equilibrium reaction would be to look at the relationship between temperature and KSP. Notice that in this reaction they give us the temperature, but if we were to change the temperature, there would be some kind of shift in the equilibrium position, and it would have a different KEQ. So let's imagine, I don't know if this is true or not, but the KEQ at maybe 200 degrees Celsius would be equal to 1.2. Okay, that's interesting because if we reduce the temperature now, the KEQ would be increased, which means it's favoring the products more, right? So that would mean that by decreasing the temperature, it's causing a shift to the right, which means that, yes, the heat term would be on this side as well. So you have lots to think about, and I will talk to you later. Bye.